Hello and welcome to part 2 of Flat Earth Answers to Jeranisms' Curve Dilemma. And what I have is a Flat Earth Clues interview number 70 from Awaken the Liberty show recorded March 27th, 2016 with Mark Sargent. The interviewer's name is Sean, and he's given us a curve question. And we're going to investigate what he sees.
Show.
That's awesome.
I know, right? And if that wasn't enough, I've already done 14 subject matter experts, ranging from everybody in the military to a lot in the professional sector. The only group we haven't gotten really is either somebody in astrophysics or NASA. They all say the same thing. They say, look, the world doesn't look like it's spinning. It doesn't appear to have any curve, and the maps appear to be wrong.
The maps certainly are wrong. I say that, I still go into this flat Earth thing, and I've classified myself as a ball Earth skeptic because I can't really prove it anyway, but I wanted to let you know that I did it after our show. I actually did an impromptu experiment. We actually went out to Pyramid Lake in northern Nevada, and Pyramid Lake, for people who don't know, is sitting at about 4,500 feet. And it's a 24-mile long lake. And that night, we were sitting on the shore. And I got to set this up because this really made me scratch my head. Now, you are allowed to have a campfire at Pyramid Lake as long as it's within 10 meters or so from the shore. Now, this is a very flat lake. It's obviously desert. And so when you have within 10 meters, say 30 feet from the shore, you're pretty much right at water level. Okay, so that's where you're allowed to have your campfires. Now, we had our campfire probably about 20 feet away from the shore, and it was just glass that night. It was absolute glass. It was a beautiful evening, and in fact, it was July 4th, so they were shooting fireworks off and whatnot. But about midnight, Mark, I did an impromptu experiment because I have a very good pair of binoculars. Now, we were at Pelican Point, and Pelican Point is a little bit of a peninsula right about in the middle of the lake, and it's about 12 miles away from the South Shore. Now, with my binoculars, Mark, I could clearly see campfires on the South Shore, which is about 12 miles away, and this really made me scratch my head.
I bet. Because at 12 miles, you would have been, and you were looking from beach to beach, basically. Beach to beach across flat water. Yeah, 12 miles, you shouldn't have been able to see that campfire. Because technically it should be on the other side of the hill, which is if people are trying to imagine this, take a basketball or any ball you're looking at, eventually something that goes far enough away is going to be on the other side of the curve. And 12 miles, if you're looking beach to beach, that's more than enough to not be able to see it. Go ahead.
No, I was going to say, if my math is correct, it's supposed to be somewhere around 36 feet below my horizon?
Yeah. So if the curvature, again, this is round Earth math, not flat Earth math, which is mainstream science will say that the curvature of the Earth that we're living on is 8 inches per mile squared, which is 8 inches per mile times itself. So that's, if it's 12 miles, it's 12 times 12, which is 144, times 8 inches, which is plenty. Let's put it that way. If that's 36 feet, that's great. But so that campfire should not be visible from where you were looking. No.
Again, it really made me scratch my head.
Okay, so here we have the scenario. Flat lake, 12 miles distance, campfire right about at water level, and you can see the fire across the 12 miles. Now, their numbers were erroneous, 36 feet. That's not correct. If you simply take the 8 inches per mile squared to 12 miles, 8 inches times 12 squared is 96 feet. Problem is, if you can see the first 3 miles with nothing blocking your view, you can see that in the daytime. If you can see 3 miles, then 3 miles of that drop are not in your way. The drop has to start afterwards. So I found a simple solution is to create a chart just like this one. And so this is the height of the observer, and it'll work for any height of any observer. You just have to set it to wherever you want. And you have to zero out that view. And the way I zero out this view is to insert column spaces and bring it down to where at 72 inches, we have to assume he's standing on the shore, raises his binoculars up to look across, so he's standing at approximately 72 inches height, tall. He can see 3 miles without the binoculars. But now you look 12 miles across the lake, and that fire becomes 54 feet below the curvature, because the curvature begins after the 3 miles. So essentially, if you take off the 3 miles that you can see, you're only dealing with a 9-mile drop, which is 54 feet. So there it is. Now, what if the curvature doesn't get in the way at 3 miles? What if it's a little bit further out? What if it gets in the way at 4 miles? Well, then we'd have to change this formula, the values in this formula here. See, we're using 3 miles squared times some value equals 72. And we're going to solve for that value as being 8 inches. And that's how we come up with it. I believe that's how they've come up with the 8 inches per mile squared. And then derived the radius from this. But we've just seen that it doesn't work. At a 3-mile distance, the curve gets in the way, 54 feet below at 12 miles, can't see it. So let's assume we put in 4 miles in the formula. At 4 miles squared, which is 16, times x equals 72, divide by 16 both sides, x is 4.5 inches per mile squared. So at 1 mile, it's 4.5 inches. At 2 miles, it's 18 inches. At 4 miles, 6 feet. And we can see, and we already know we can see, we're just deciding we can see at 4 miles. Now what this does is this changes the radius of the Earth to 7,040 miles. Because as you can see, using the hypotenuse formula, square root of r squared plus distance squared minus the radius, 4.5 feet, 4.5 feet. 18 inches, 17.999. 6 feet, 5.999. So we have a radius of 7040 in order to come up with this 4.5 inches per mile squared. But let's see if we can still see the fire. So we take our miles that we can see, go down to the miles we're looking for, and that fire should be 24 feet below the curve, well beyond sight. And that's at a much larger Earth. All right, let's take it one step further. 5 miles. Let's presume we can see 5 miles. Plug in the new numbers. 5 squared equals x equals 72. X equals 2.88 inches per mile squared. And here is our, and that makes a radius of 11,000 miles. Earth. Zero out our 6 feet so we can see the block begins, and at 12 miles the fire should be 11 foot 9 inches below the curve. Still out of view. Binoculars and telescopes do not erase the curve. They just make what you're looking at easier to see. So at 5 miles visibility before the curve comes in, it is still not there. Take it one more step. 6 miles. We presume that we can see 6 miles before the curve gets in the way of your view. 6 squared 36 times x equals 72. Divided out, x equals 2 inches. And that's 2 inches per mile squared. But in coming up with 2 inches per mile squared, that gives us a radius of 15,840 miles. Taking our 6 feet, zeroing out our height because we can see 6 feet or 6 miles, come down to 12, and the fire would still be 6 feet below the curve. And as he said, it's a very flat lake. The fire would not have been any more than a foot or so up the beach, a foot or so in altitude above the waterline. Still not visible. And that's out on a world 4 times the size of the one they say we're on. So it is my estimation, my presumption, and this might be the proof we need, that 3,960 miles, roughly, was derived from being able to see 3 miles and calling it a 72-inch drop, when what we see at 3 miles is a 72-inch rise. The horizon rises to your eye level. As above, so below. We see 72 inches up. We're told it's 72 inches down. But the visibility isn't there. Is this the proof we need? Maybe. Stay tuned for part 3, where I cover perspective and why things at a distance are below the horizon, above the horizon, at the horizon. And how not only how binoculars and telescopes work, our vision works, but how microscopes work to do the exact same thing. Stay tuned. Thank you.